In this example problem, we're going to determine the stresses at surface at midspan using the force-in-the-tendon approach for the section shown below. And we're going to use the three different types of section properties that we've been discussing in the module so far. You can see some of the properties that we'll need. We have our concrete strength at release and at service, and our ultimate strength. And then we have some of our gross section properties, some of our strand properties, our information for our time effects, and in this case, we're given our loading at the section of interest, our self-weight moment, our moment from our superimposed dead loads, and our moment from our live loads. The first thing that we can do is we can find our different material properties. Here we have our modulus at release, just using our ACI equation, our modulus for the concrete, or the ultimate strength of the concrete, and our effective modulus, which takes into account the effect of creep with our given creep coefficient. We also have our gross section properties. They're given in this case, and they'll often be given for precast sections. If we don't have them here, then we would, of course, need to calculate them. And we can find our eccentricity due to the gross sections here. So we have that, just our D minus our Y top gross is going to be 9.5 inches. Our first step is to calculate our pre-stress losses. And we're going to use the PCI Design Handbook approach from the 7th edition of the PCI Design Handbook. The elastic shortening losses can be calculated the same way that we have in our previous example. So we'll need our force in our strands at jacking, so before transfer. So our 202.5 KSI times our total strand area. And we can plug that in with our self-weight moment to calculate the stress in the concrete at the level of our pre-stressing strands. We'll find that in this case to be 0.583 KSI. We can take that times the ratio of our modulus for our pre-stressing strands divided by the release modulus for our concrete, and we'll get an elastic shortening loss of 4.6 KSI. If we take our strand stress before transfer minus that elastic shortening loss, so 202.5 KSI minus 4.6 KSI, we'll get the stress in our strands after release or after transfer happens. And that stress is 197.9 KSI. We take that times the total area of our pre-stressing strands to give us the force in our strands after release of 128.8 kips. Next, we need to find our pre-stress loss due to creep and our pre-stress loss due to shrinkage. We're given our moment from our deck load, or our superimposed dead load here, of 221 kip inches. So we can use that to find the stress at the centroid of the strands due to this, this moment. So we have 221 kip inches times 9.5 inches, our strand eccentricity, divided by 17,517 inches to the fourth, will give us a stress here of 0.120 KSI. We can use this stress with some of the values that we had calculated before to calculate our creep loss. So our creep loss is going to be equal to 2.0. We're assuming that we have normal weight concrete, so we have a KCR of 2.0 times 28,500 KSI divided by 4,415 KSI times 0.583 KSI minus 0.12 KSI. This will give us a creep loss here of 6.0 KSI. Next, we need to find our shrinkage loss. And to do this, we need our volume to surface area ratio, which is about equal to the ratio of our area to our perimeter. So we have our area given for our gross section, but we need to find our perimeter. And to do that, we need to add up all of our different faces that are exposed to the outside. So we have 12 inches plus 2 times 16 inches. So this is coming up our sides now. And then we have 20 inches, do our top side, plus 2 times 8 inches. We have our two sides here. Plus we have this distance here is 4 and 4, so 8 total inches. So we'll add in our 8 inches. And this will give us a total perimeter here of 88 inches. So our volume to surface area ratio then is our area, 352, divided by 88 inches, which will be equal to 4 inches. We can use this with our given relative humidity to find our shrinkage strain. So our shrinkage strain is going to be 8.2 times 10 to the negative 6 times 1.0, our K shrinkage for pre-tensioned components, times 1 minus 0.06 times 4 inches, times 100 minus 75 will give us a shrinkage strain here of 0.156 times 10 to the negative third. We can take this shrinkage strain times our modulus for our pre-stressing strands, 0.156 times 10 to the negative third times 28,500 to give us a shrinkage strain of, or a shrinkage loss of 4.4 KSI. So this is our loss due to shrinkage and our pre-stress loss due to creep. Our next step is to find our relaxation loss. And to do this, we'll use two different tables that are provided in the PCI Design Handbook. First, we have our strand type, which we have grade 270 low relaxation strands. This is the type of strand that will typically be used today. So we have our K relaxation is going to be equal to 5,000 PSI or 5 KSI. Our J is equal to 0.040. Next, we need to find the ratio of our initial pre-stressing stress to the ultimate stress. So we have 202.5 divided by 270 KSI, which is equal to 0.75. And this is a typical ratio. So we can come down here to our table and find that our C for low relaxation strands is going to be equal to 1.0. So we can plug in these values, the K relaxation, the J, and the C, with the other losses that we had calculated before to calculate our relaxation loss. So here we'll have 5 KSI minus 0.04 times 4.4 KSI plus 6.0 KSI, our creep loss, plus our elastic shortening loss, 4.6 KSI. And all this is times 1.0 for our C factor. And this will give us a pre-stress loss due to strand relaxation equal to 4.4 KSI. We can then add our shrinkage loss, 4.4 KSI, plus our creep loss, 6.0 KSI, plus our loss due to relaxation, 4.4, to get our total long-term losses, which will be 14.8 KSI. And we can add those long-term losses to our elastic shortening loss, which is a short-term loss, to get our total pre-stress loss. So this will be 4.6 KSI plus 14.8 will give us a total loss of 19.4 KSI. So these two values, the long-term loss and the total loss, we'll use to find our stresses on the next couple slides. Before we can find our stresses, we need to calculate all of our required section properties. And first, we'll find our long-term net section properties. We'll find these the same way that we did in our previous example, where we have our gross section and we're removing the area of our pre-stressing strands. So our net area is just our gross section minus the area of our pre-stressing strands. We can find the distance from the top to the centroid of our net area the same way that we did before. So gross area times the distance from the top to the centroid of our gross area minus the area of our pre-stressing times the distance from the top of the section to the centroid of our pre-stressing strands, and then divide all that by our net area. Then we can find our moment of inertia the same way that we did before, and our eccentricity the same way that we did before. Again, I'm differentiating between short-term and long-term here. If you have non-prestressed steel, you need to transform that non-prestressed steel into an equivalent concrete area. And you need to make sure that you're using either the modulus for the concrete at release or at final, or the effective modulus of elasticity for the concrete, depending on what type of loading you have. So here, we don't have any non-prestressed steel, so the short-term and long-term net areas or net section properties will be equal. We can find our short-term transform section properties also the same way that we did in the previous example, where we transform the area of our pre-stressing into an equivalent concrete area using our modular ratio, which is the ratio of our pre-stressing modulus to our modulus of our concrete using the ultimate strength. And then we can add that pre-stress area to our gross area to get all of our different short-term transform section properties. So here we have our A transform short-term, so our gross area plus n minus 1 using our short-term modular ratio times the area of our pre-stressing. Our Y transform short-term, so the distance from the top to the centroid of our transform section. So A gross times Y top gross, n minus 1 times A area of our pre-stressing times the distance from the top to the centroid of our pre-stressing, D sub P, and then all that divided by our transformed area. And we can find our transform moment of inertia the same way that we did before, using our gross moment of inertia plus our AD squared component. So our A gross times a D squared component, the distance between the gross section and the transform section, and then our A D squared component for our pre-stressing. And then finally, we can find the eccentricity of our strands with our short-term transformed section. We can do the same thing with our long-term properties. Here, our modular ratio we find by dividing our effective modulus for our pre-stressing divided by the effective modulus for our concrete. So this takes into account the strand relaxation and the creep effects. So transforming our steel, we'll get an area here of 352 plus 18.9 minus 1 times the area of our pre-stressing, 0.651 inches squared, which will give us a transformed area, 363.7 square inches. Our transformed centroid, the distance from the top to the centroid of our long-term transform section will be 352 times 10.5 inches plus 18.9 minus 1 times 0.651 square inches times 20 inches, distance from the top to the centroid of our strands. And this is all divided by 363.7 square inches, our transformed area. And this will be 10.81 inches. So you can see our centroid of our gross section, 10.5 inches. Our transform pre-stressing is pulling that centroid down, so we have a larger distance from the centroid, or from the top to the centroid of our transform section. So conceptually it checks. Next, we need to find our transformed moment of inertia. So we have our gross moment of inertia, 17,517 inches to the fourth, plus our AD squared component, so 352 times 10.81 minus 10.5 squared, plus our AD squared component for our transform pre-stressing. So 18.9 minus 1 times 0.651 square inches times 10.81 minus 20 squared. So this will give us an I transformed long term equal to 18,537 inches to the fourth. We can find our strand eccentricity the same way before, taking our D minus our Y top transformed, and we'll get an eccentricity shown there, 9.19. So these are our long-term transform section properties. We're now ready to calculate all of our stresses from all of our pre-stressing using our final pre-stressing force after all of our losses and all the applied moments. So we're first going to use our gross section to calculate our stresses. So our top fiber stress, remembering that our sign convention is going to be negative, is compression. Our pre-stressing is going to cause a compressive stress in the section, so the axial stress from the pre-stressing will be compression, so we have a negative sign there, 119.2, divided by our gross area, 352 square inches, plus the eccentricity of our strands is going to cause tension in the top, so we're going to have a positive sign here. So we'll have 119.2 kips times our eccentricity, 9.5, times the distance between the centroid and the top of the section, 10.5 inches, divided by 17,517 inches to the fourth. Next, we have all of our flexural stresses from our applied moments, and I'm going to group these together because we have the same gross properties for all these. But you can see when we use the net section, net transformed or transformed approaches on the next slides, we need to keep these separate because we'll use different section properties for each one. So here, the moments, applied moments, are going to cause compression in the top fiber, so we have a negative sign. And we have our moments of 674 kip inches plus 221 kip inches, plus our live load moment, 735 kip inches. And this is all times 10.5 inches, the distance between the centroid and the top of the section, divided by 17,517 inches to the fourth. So here we'll get a top fiber stress equal to negative, which is compression, negative 0.637 KSI. Next, we can do the same thing, except with a different distance component. So the distance from the centroid of our section to the bottom fiber. So FCB is going to be negative. Our pre-stressing is still causing compression in terms of axial stress. So negative 119.2 kips divided by 352 inches squared. This time the eccentricity of our strands is causing compression in the bottom fiber, so we have a negative sign here. So we'll have negative 119.2 kips times our eccentricity, 9.5 inches, times our distance component between the centroid of the section and the bottom fiber, 13.5 inches. And then all this times our gross moment of inertia, 17,517 inches to the fourth. All of our moments are going to cause tension in the bottom. I'm going to group these again for the same reasons as above. And we'll have our self-weight moment, 674 kip inches, plus our moment due to our superimposed dead load, 221, plus our live load moment, 735 kip inches. And then this is all times 13.5 inches. And then we divide by our gross moment of inertia, 17,517 inches to the fourth, which will give us a bottom fiber stress here of 0.045 KSI. And you can see it's positive, so we have tension in the bottom fiber. So here's the bottom fiber stress and the top fiber stress using our gross sections. On this slide, we can see our stress calculations if we use our net and transform sections. If we're using net and transform sections, then we need to use the force in the tendon after all of our pre-stress losses. So we need to take off our total pre-stress loss from our stress in the strand before release here. You can see here in this equation, I show you how to calculate your stresses using the net and short and long-term transform sections. We'll use our net section properties for any self-equilibrating forces. And this includes the axial and flexural stresses from our pre-stressing. And it also includes the flexural stresses from our self-weight moment. We'll use our long-term transform section for any sustained loads. So we have our sustained superimposed dead load there. And we'll use our short-term transform section properties for any immediate load or short-term load. And in this case, that's only our live loads. So you can see, plugging in all of our different values, we'll get a stress in the top fiber equal to negative 0.628 KSI. So negative means we have compression in the top. We can do the same thing in the bottom fiber, remembering still to use our net section properties for any self-equilibrating forces, our pre-stressing and self-weight, and our long-term section properties for our sustained loads and short-term section properties for our immediate loads. And we'll find a bottom fiber stress equal to 0.014 KSI. So we have tension in the bottom. On this slide, we find our stresses using our transform sections. If we're using only our transform sections, then we need to not remove our elastic shortening loss. Our elastic shortening is taken care of by using our transform sections. So we only need to take off all of our long-term losses when calculating stresses. So here, just taking off our long-term losses, we'll get a force in the pre-stressing equal to 122.2 kips. We can then use our transform section properties for any sustained loads. So this includes our pre-stressing, our self-weight, and our superimposed dead loads. So here you can see our long-term transform section properties we use for our pre-stressing, for our self-weight, and for all of our other superimposed dead loads or sustained loads. The short-term transform section properties we'll only use for our immediate loads or our live loads. So you can see plugging in all those values, we'll get a top fiber stress of negative 0.639 KSI and a bottom fiber stress here of 0.054 KSI. So tension in the bottom and compression in the top. Here we can see a comparison between the three different methods. First, we can see the compression limit if we're looking at our service loads, so our pre-stress plus our total loads, and our tension limit at service, so 7.5 times the square root of F prime C and 0.6 times F prime C. So we can see our compression and tension limits. And then we can see a summary of a comparison between the stresses calculated using our three different methods. We can see that our compression stress is a little smaller if we use net transformed section, and our tension stress is also a little smaller. The gross and transformed section in this case have very similar stresses. On this slide, we can see a comparison of the three different approaches with different pre-stressing areas and with different moments. The first case, we're increasing the pre-stressing amount, and you can see that when we increase the pre-stressing amount only, the compression in our bottom fiber is going to be higher when we use the net and transform section. This is because we use our net section to find our stresses due to pre-stressing, and our net section doesn't include any pre-stress area. Our transformed area, on the other hand, and gross section, so gross section does include the pre-stress area in the section, and our transformed approach actually transforms our pre-stressing in resisting, or transforms the pre-stressing to resist the forces from our pre-stressing. So you can see that stress is going to be less because we have more area and a higher moment of inertia resisting that pre-stressing. If we come though and increase our live load moment only, we can see that our stress is going to be less for our net transform section. And this is because, again, the pre-stressing is going to have more of an effect on our net transform. So we're going to get more benefit from our pre-stressing if we use the net transform section approach. And then finally, if we increase the pre-stressing area and our live load moment, you can see that, again, the net transform section approach is going to have smaller stresses because it will give us more benefit from our pre-stressing strands. And the other thing you can see is there's not really any difference between the gross section and the transform section approach. So in general, using the gross section approach is a reasonable approximation. So that concludes this example.